When we build a Taylor polynomial, we have an effective way of approximating a function using a finite number of terms. And we know that in general, if we let the number of terms increase, we get a better and better approximation. In this video, we're going to take that idea one step further and use an infinite sum to approximate functions. These sorts of sums are called power series. Recall that for a geometric series, the sum from n equals 0 to infinity of r to the n, we know that that series is exactly equal to 1 over 1 minus r when the absolute value of r is less than 1. R can be any real number in this case. So what that means is that we can replace r by the variable x. In that case, we know that the sum from n equals 0 to infinity of x to the n is going to equal 1 over 1 minus x, as long as x is some number that is between -1 and 1. In other words, its absolute value is less than 1. This then tells us that the function f of x is equal to 1 over 1 minus x is the same thing as the series, the sum from n equals 0 to infinity of x to the n, for all values of x between -1 and 1. We can generalize this idea from geometric series to create something called a power series. A power series is one written in the form the sum from n equals 0 to infinity of c sub n times x minus a to the n. Let's look at a few definitions related to power series. First, the c sub n's at the beginning of each term are called the coefficients. A is the center of our power series. We saw in our geometric example that the series may not converge for every possible value of x. Therefore, the x values where the series does converge are called the interval of convergence. The radius of convergence, then, is going to be the distance from A to the boundary of that interval. We'll see that the ratio and root tests are invaluable in helping us determine the interval of convergence and the radius of convergence for a given power series. Let's take a second to remind ourselves what the ratio and root tests tell us before we try a few examples. The ratio test tells us that if we take the limit as n goes to infinity of the absolute value of the n plus first term divided by the nth term, and that limit is less than 1, then we have absolute convergence. If the limit equals 1, the test is inconclusive, but if it's greater than 1, we know for sure that our series diverges. The root test is similar. It tells us that if we take the limit as n goes to infinity of the nth root of the absolute value of the nth term, and that limit is less than 1, once again, we have absolute convergence. If it's equal to 1, the test is inconclusive, and if it's bigger than 1, we have divergence. Our goal then in determining the interval of convergence and the radius of convergence will be finding the values of x that force these limits to be less than 1, finding the values of x that make them equal to 1, and knowing we need to do a little bit more work there, and then ruling out all the values of x that make these limits bigger than 1. Let's see if we can find the radius of convergence for the series, the sum from k equals 0 to infinity of x minus 1 to the k over k factorial. The k factorial is a signal that we probably want to use the ratio test. So let's examine the limit as k goes to infinity of the absolute value of the k plus first term, which would be x minus 1 to the k plus 1, over k plus 1 factorial, divided by the kth term, which is x minus 1 to the k, over k factorial. We know that we can flip that denominator over to give us the limit as k goes to infinity of the absolute value of x minus 1 to the k plus 1 over k plus 1 factorial times k factorial over x minus 1 to the k. We can simplify that. That is the limit as k goes to infinity of x minus 1 over k plus 1. We still have our absolute values on there. However, regardless of the value of x, this limit, as k goes to infinity, is 0. 0 is less than 1, so that means that this thing converges absolutely regardless of the value of x. When that happens, that means that you have an infinite radius of convergence. Our radius of convergence, r, is infinity, and our interval of convergence is going to be negative infinity to infinity. Our last example had an infinite radius of convergence, meaning that the series converged regardless of what value of x we put into it. That's not always the case, though. Let's take a look at this example and see if we can observe some different behavior. So we can see we have a kth power here, which is a signal that we probably want to use the root test. Let's start, however, by rewriting this series. So we can write the sum from k equals 0 to infinity of negative x over 10 to the 2k as the sum from k equals 0 to infinity of negative x over 10 squared to the k, which then becomes the sum from k equals 0 to infinity of x squared over 100 all to the k. We're going to use the root test, so we're going to take the limit as k goes to infinity of the kth root of the absolute value of x squared over 100 to the k. That is the limit as k goes to infinity of the absolute value of x squared over 100, but those terms are always positive, so we're going to see that this is the limit as k goes to infinity of x squared over 100. That limit equals, because it has no k's in it, it equals x squared over 100. We know from the root test we get convergence when x squared over 100 is less than 1. That tells us that x squared is less than 100, which means that x has to be between negative 10 and 10. So on the interval negative 10 to 10, we are guaranteed convergence by the root test. However, notice that when x equals 10, our limit is then equal to 1, which is the inconclusive case. So we have to do a little bit more work. So let's see what happens when we plug 10 into our series. Then it becomes the sum from k equals 0 to infinity of negative 10 over 10 to the 2k, which is just the sum from k equals 0 to infinity of 1, which definitely diverges. An infinite number of ones being added up will not converge. Similarly, if we so this was the case when x equals positive 10. If we do the same thing for x equals negative 10, we get the sum from k equals 0 to infinity of 10 over 10 to the 2k, which also diverges. So what we now know is that our radius, or our interval of convergence, is negative 10 to 10. It's an open interval, and our radius of convergence r is equal to 10. So far we've seen an infinite radius of convergence, a power series that converged no matter what value of x we plugged in, a finite radius of convergence, one where we could only plug in values between -10 and 10 and get convergence. We're going to look at one more case here. Hopefully by now you have some sense that if we want to evaluate the sum from k equals 0 to infinity of k factorial times x minus 10 to the k, that we likely should use the ratio test because of the factorial term. So let's examine the limit as k goes to infinity of the k plus first term, k plus 1 factorial times x minus 10 to the k plus 1, all over k factorial, the kth term, k factorial times x minus 10 to the k. The simplification is pretty straightforward, so we're taking the limit as k goes to infinity of k plus 1, the absolute value of k plus 1, times x minus 10. This thing is going to be infinite when x is not equal to 10. When x equals 10, we have this infinity times 0 case. Things get a little weird, so we're going to have to look a little bit harder at this. But we now know that the only place this might converge is when x equals 10. That tells us that we have a radius of convergence of 0. So the only thing that's left for us to do is figure out what happens when x equals 10. In that case, the series becomes the sum from k equals 0 to infinity of k factorial times 0 to the k, which is just 0. So we do in fact get convergence at 10. So our interval of convergence is just the value 10. It's not really an interval. And our radius of convergence is 0. The three cases we've seen here summarize all of the possibilities. We can have an infinite radius of convergence, a finite non-zero radius of convergence, or a zero radius of convergence. These give us a procedure we can use in general in order to determine the interval of convergence and the radius of convergence for a given power series. We're always going to start with the ratio or root test. We'll make that determination based on the structure of the series in question. When we've completed the test, if the limit is less than 1 and does not include any x's, then we know our radius of convergence is infinite. If the limit is greater than 1 and does not include any x's, then our radius of convergence is 0. If the limit involves x, then we have to figure out which values of x make the limit less than 1. Our last order of business then is to check any x values where the limit was exactly 1 or where it was undetermined, as in a 0 times infinity case.